Thank you for the opportunity. As you all know, this has been one of the annual meetings that we have every year, where many of us who have been presenting our ongoing developments have been talking about this over and over again. So there are certain parts of which I hope many of you are already very familiar with. When I started giving these lectures and I was coming to these conferences in the beginning, we spent a lot of time on developing how we are going to talk about the area or the discussions on these areas. Now after say about this is the fourth year that we are doing this conference, I hope we will not have to really go back too much into the details. However, I will try to see how we can present our work in a way so that it looks reasonably understandable. So the work that we present here would not have been possible without the help of the students. So that is one of the biggest advantages of having a program in which we have a lot of undergraduates as well as PhD students working. And today I'll be talking about a little bit about the new area of dabbling, where we have gone into few optical cycle pulses interactions to see how that would be bringing us to the future. So as our work goes, most of it is concentrates on the properties of light and its interaction. And so typically we use a laser which generally of the kind of an ultra short pulse, as we call it. And in this domain, when we have a laser, the output of the light taken out is the one which is coming out as a very short burst of light, and it has very strong characteristics which are different from the ambient light, as we call it, like the light that you have from the light bulbs or whatever is powering us up here. And the random phases of all the light waves are the ones which are important there. And so at any point of time, if you measure the irradiance versus time, this kind of a graph that you will be generating. However, if you have a laser, then all the phases are locked, and so at a given point of time, you get a very short pulse of light, and that is the ultra short pulse of light where all the phases are locked up. So if you want to resolve in time, you will find that they are all at a given point of time coming or appearing at the same time. And that gives rise to all these phenomena where we call that the destructive interferences do not let any light come through in these parts, and only the part where all the phases are properly phased, the light has all the phases properly phased, we get pulses. Typically, the oscillations within the envelope is so high that we are unable to resolve these oscillations, and what we eventually get out of these kinds of a pulse is the envelope effect of the pulse. And that has been the typical way that we have looked at light pulses as we have made our foray into this area. And generally, our research area, just to give you a recap, has been to take pulses of light, the broadest possible ones as we can go to, and so we are more and more interested in shorter and shorter pulses, because we can get both better and better bandwidth over which the light exists, and playing with that bandwidth so that you can do some applications. So one of them is information technology, as we know, and the other parts of the things remains. And this is how I was trying to tell you that the oscillations within the pulse essentially do not matter whenever you try to measure it. It's the envelope profile which shows up in most of the commercial lasers that we use. So this is a typical 180 femtosecond laser coming out of a commercial laser at 730 nanometers, which is an infrared laser. Happens to be a naturally emitting laser from a titanium sapphire crystal, and so this is quite a popular laser as of now currently used. So our research activities has been mostly in the region of femtoseconds, which is some orders of 10 to the power minus 15 seconds. Units are in the 10 to the power minus 15 seconds. And one of the reasons why we do these activities is to try to see if we can do better chemistry, representing the chemistry department, where we would like to actually excite a single bond and see if we could really make that bond vibrate to a level that it can break down. Unfortunately, that's not what happens. These brings effective spring systems. The energy of the bond is quickly transmitted to the entire molecule, and so whatever you would be doing by just heating up a system is what you end up by using thousands of dollars or quite a expensive laser system. So this kind of difficulty was one of the things which was seen way back in the 80s, and a parallel area of development of how this process can be looked at has developed in the area of chemistry, and that's one of the fields where it all started off. But this has very interesting implications, because this sort of lets you ask questions whether you can utilize and backtrack these activities to look at the other areas of research which has developed over the years. One of the very simplest ones, before I move out of this slide, is to say that rather than have the molecule interact on its own with the light and disperse its energy in its own particular pathway as it would do, you could make this problem into a force oscillator problem, where you are dictating the terms of how this property evolves rather than making the molecule decide what it is going to do. And that is one of the areas which gives rise to nonlinearity, where the control knobs come more handy than what they are otherwise in this linear kind of world. So what we enter then therefore is the area of quantum mechanics, where mostly we are talking about the wave or probability phenomena and the possibility of our bond vibrations being taken care of is given by typically in the textbook form of looking at breaking them down into harmonic and non-harmonic terms and looking at them. Mostly when we deal about it in classroom lectures and other places, we are not worrying about the translational part, because they can be looked at separately. However, it is interesting to note that whenever we look at intramolecular events, there is always an intermolecular or a translational component associated with it, and there are forced ways of getting rid of one over the other. But when we talk about quantum computing, this is one of the areas where both of them become important, because you would really, if you are going to use a molecule for doing a computing for you, you would like to have the molecule transmit that computing to the next level. And so it needs to somehow also couple or have a translational activity which is under control. So you would not just want to control the intramolecular aspects, but also would like to control the intermolecular or the translational motion of these events. And so it becomes a larger or a more difficult task than it is for even the chemists for these cases. Here are certain control knob issues that has been presented in this audience before also. So there are typical terms which are used, which are sort of called the laser polarization, the temporal aspects of the laser, frequency concepts, and we can ask questions as to how these terms or parameters are important or are within the domain of what we know about these things. One area where we have spent a lot of time has been to change how the electric profile or the laser component itself is, and this becomes an area of a lot of interest, because the pulse that we are talking about here is a very short pulse, and for such short pulses it is difficult to directly think about ways to do anything with it. And so we have developed techniques, now these are fairly old, where we have gone into the Fourier domains and we have modulated by using standard modulators to get to our pulses and shapes that we would like. And these linear filtering schemes work very well, and they are borrowed specifically from electrical engineering principles, and they work very well. There is no big surprises in these efforts. It's just that it becomes a tool which is much more effective as you go into shorter and shorter pulses. And you can couple this into, as I said, into a device where the motion of the molecules can be frozen, and this is one of the ways where you can not worry about the motion. because you could have a gas phase of system where everything is made to move at a given velocity by velocity selection or by keeping the environment under completely closed control. And these kinds of beam chambers and devices can be generated. This is one of our work which we have done. We basically made a pulse nozzle valve of a beam of molecules which are kept under a particular environment, and then when you have a laser beam cross it, then we have a perfect control on the molecular property, and we are at that point of time not letting the motion of the molecules bother us. It is only the intramolecular events that we discuss and deal with it. This has been a standard way of dealing with these events, and yet it has become possible from these studies to look at systems which are quite complicated, and the ideal situation which works very well in parallel to the quantum computing world is the two-level system, because we would like to consider have a quantum bit, which is the qubit, connected to the two-level system. It works very well, and you can actually go ahead and define your Hamiltonian parameters in such a way so that you are allowing the field to be to absorb the fast oscillating part, and you will be only worrying about the slowly varying component of the field. And so these are known as rotating wave approximations, where the fast oscillation within the pulse is sort of not to be worrying about. To us, it's like saying the relative motion is what we are interested in, sort of like you and us, me and you are all in the relative frame of the Earth's motion. So it doesn't matter how we are doing the activity, and so you can get rid of these and you can go to frequency modulated frame and you can write down the Hamiltonians like this. It evolves quite nicely here, and the story turns out to be quite easy. You can even go ahead and do some other expansions to show that it can be evolved further, and the applications of these pulses can be looked at by just solving the Liouville equation, integrating them. And with these standard techniques, you can see the typical oscillations, or the Rabi oscillations as they call about, for a two-level system where it is just the excited and the ground state energy flopping which happens as you apply the field. And that depends only on the area of the applied field. So for such a pulse where the oscillation within the laser is immaterial, these are all expected results, and that has been around for many decades now. However, when you talk about pulses where you are going to shorten the width to such a level that the internal oscillation of the pulse becomes important, then it is difficult to assume that the frames of reference can be taken to a level where you can ignore the internal oscillations. And the first question therefore arises is, how important are these internal oscillations of the field when you have a pulse getting shorter to a level, or having wavelength longer to a level that there are cycles which can be counted within a pulse of light. These typical pulses are known as few cycle pulses. They need not be very short pulses. Even a few femtosecond pulses in the infrared wavelengths can have a few cycle limit, because as you know that you at least need one cycle pulse to define one cycle within a pulse to define a particular pulse. Otherwise, your Heisenberg uncertainty principle takes over, and you will not have anything which is known as a definition of a pulse. So within that definition, if you would like, you would at least have to have one oscillation sustaining within the pulse. And as you do this wavelength versus where the energy of the pulse versus where the width of the pulse is, you will be able to find that for infrared regions, for few femtosecond pulses, you are already in the region where oscillations are important. You cannot just ignore them. When you do that, then the question starts as to what is the point where the cycling effect, or this additional nonlinearity which is coming because of the oscillations within the pulse, is going to become important. And that is the part where we now have looked at, and we have found that when we apply, so if we ignore the fact that we have gotten to this regime where my pulses the cycle within the pulse is countable, and we still apply the rotating wave principle, then I produce a result where it looks like the oscillations, the Rabi oscillations are spacing out further. And you might think that this is just a little bit of a change which has happened because of this effect. However, it turns out that that is actually a wrong way of looking at it, because we can no longer, as I just mentioned, use the rotating frame approximation. And if you then apply the brute force technique of actually solving the problem, you find out that this oscillation that you see is no longer that easy to look at and interpret. It is all over the place. And that is one of the ways of looking at it. This, by the way, it shows that if 0 is the point where it is exactly on resonance, so your two-level system has an exact resonance energy to address that. And if you are going away on both sides, it essentially means you are having energy which is not equivalent exactly to match the energy. It is close enough, but not quite. And we can show that it is possible, as it is shown in other cases, that there is an inversion which is possible to a certain band, to a certain width, even if the energy doesn't match exactly. And that is known as an inversion profile. So based on that, you would see that there is a drastic difference between the two. When we saw this first result, we thought that the cycling of the pulses, cycles within the pulse, are so important that we cannot come up with any information or cannot do anything about it, and therefore maybe until today nobody has done much of these experiments. Few things about experiments on this area. One is that these are already highly energetic pulses. To be able to control their energy very carefully, to see a system evolve through a region of energy, experimentally is not an easy experiment to start with. And if there is no motivation, then obviously somebody would not want to do these hard experiments. So it was our first aim to see whether by any means these experiments have any sense to be looked at or not. So when we saw this drastic difference, then we were curious, because even if it might not be a worthwhile experiment to do, it might be useful to try to now understand what is going on. So the next step we did was we basically took various different shapes, because one thing which came out by looking at this previous picture is that perhaps there is no effect of the overall envelope of the pulse anymore, because now I have only a few oscillations, and so the field oscillating is perhaps dictating the whole story, and therefore my amplitude profile of the pulse has no meaning. And so this limit, this is actually a very strict limit of only 6 cycles sustaining within a pulse. Typical pulse that we are used to has 10 to the power 6 oscillations within the pulse. So we are talking in terms of 10 to the power 6 oscillations versus only 6 oscillations. So this is a very brute force way of looking at things, that we are really asking a situation where it will definitely fail to a point where it doesn't fail. So we wanted to slowly look at the problem, and we looked at, so the first question to ask was to find out whether the envelope profile makes any difference or not. So we tried different envelope profiles. So some of the very simple ones is like a cosine square, which is just a cosine function. As we see, it looks horrible as you have only one oscillation here, one oscillation within the pulse. And then as we increase the number of oscillations, so it goes to 6, 11. So this number essentially says how many oscillations, how many cycles. And so here it is 36, which is now getting to a point where the Rabi oscillation looks very good up to quite a large resolution. This number here is 300. 300 in these units is a very large number. So there is enough energy, theoretically we can look at any number, but there is enough energy that people will not really have to go anything beyond that. Typically, as we talk about in terms of nonlinearity, any single full oscillation of this is good enough to talk about nonlinearity. Because nonlinearity starts the moment you can see the population coming back to itself. Ground state coming back to itself is something known as self-induced transparency, which is sort of a very highly nonlinear way of looking at things. So the fact that we are all the way to some 30 or 40 oscillations in Rabi
which means that we have enough energy. So for all practical purposes, when I have reached to about 30 to 40 oscillations sustained within a pulse, I have gone back to a region where I could talk about the pulse as we know it, in terms of the oscillations within the pulse are very large, and so the envelope is an important parameter, and we know that quite well. So the area theorem would perhaps work there. And so what we did was we tried to see how these things matter. So what we are now doing is we are trying to define something known as a nonlinearity parameter, or deviation from what we call it the point where the oscillations within the pulse matter to a point where the oscillations do not matter. So what we are trying to define is a point from where we would see these nice little oscillations start having other imperfections coming in. So for example, for n equal to 6, we see up to 3, we don't have any problem. When we go to the fourth one, we have a problem. We have these other wings coming in. So we have sort of connected the number n with from where these deviations have started. And with that, we have drawn a graph here. So this is our graph for the cosine function, and these are the number of cycles. This is one way of trying to quantify how one is affecting the other. And so then we look at the other envelopes. So this is a Gaussian envelope, and the story generally continues. The patterns are different and all that, but what we find is that there is a correlation that we can build up, and for all these different functions, so this is hyperbolic secant, and you get correlations, and then what we do is we actually plot them. This is something called von Mises. This is a parameterized wave function where you can put the parameter k as different numbers. The largest possible number makes it closest enough to the Gaussian, whereas the smallest possible number makes it farthest away from being a Gaussian. Whatever way it is, this is sort of another way of looking at pulses. So when we plot them, one of the biggest difference which we find is that as we change the envelope profile, the pattern changes, which means that our previous assumption that the envelope profile does not matter is a very hard assumption. That is also not quite true. Now, when this result came, it was actually a lot of satisfaction. The reason being, there is a very fundamental theorem of electrical of information technology which says that for any well-behaved function, even if you know only the start of the function, you can predict the entire function. That is because for any well-behaved function, there are properties which are well defined, and so if you can catch a little bit of the function, you can essentially tell everything about the function. And therefore, all these anomalies where they talk about that, subluminal information transfer and all that, there were some times where there were difficulties in understanding them. It turned out that it was very simply explainable, because it was possible to explain on the basis that if it is a well-behaved function, knowing a little bit of it can always give you the entire information, and so there is no subluminal information flow. So it was important for us to realize that amplitude actually matters, even though, and in this limit we were having difficulty in understanding that the amplitude would not matter. So this has been our first kind of effort to look at this area. It turns out that this area now opens up a lot of very interesting problems that we are now looking at, including the fact that as you have pulses which are in the middle domain, where we know that both of them are important, how does one influence the other, and whether multiple pulses are going to have interesting further effects on the system which can be amplified or which can be acted as something else or not. So this was one of the comparative studies which were done at that time with this work. And the present status as of now is that there are distinctions. Obviously, the area under pulse is no longer the most important parameter as it is for the many cycle envelope. However, the envelope effect still persists even in the few cycle limit. The measure of the nonlinearity is one of the ways that we have done. We have come up with something which we think is consistent, but this can obviously be improved better and can be looked at in many different ways. So this is one of the work in progress which is going on. The other impacts of these kinds of studies, or the overall laser property change. So what we generally have been focusing on, as I would like to tell you, is that we have been trying to change the property of the laser and seeing the effect as a result of that. So the other impacts of this study have been in many areas. For example, in this particular example, I show you that as you actually change the pulse width, it also has a spatial change width. And that has a very important connotation in microscopy. And so one of the things which we have been able to successfully demonstrate, that the focal plane over which the pulse exists gives us the Z resolution of our microscopic image. And so we can essentially use a pulsed laser confocal microscopy, which is essentially imaging only the point where the focus happens compared to all the other regions where the pulse could be. And so shorter of a pulse you can be, the shorter in space it will be, and so you will get a better and better resolution in microscopy. So that is another application that you can look at. In fact, this is a little bit more of the same picture, which shows that you can in fact go through a so this is just a bead which is being looked at by the pulse of light at different delays. Now this is typically done in a confocal microscopy. It's also a very powerful scheme where you would be moving the light, moving the slide to show that you are able to go through the different stages. So this is known as dissection in the Z dimension dissection. So this we can do just by delaying the pulses. So that makes it an immovable setup which can be sometimes very, very effective. So these kinds of pulses, I mean not just these short pulses, any femtosecond pulse can also have very important other impacts. For example, once again in microscopy, we have had situations where the fluorescence of overlapping chromophores can be a problem. And by using pulses which are coming at different delays, and in this particular case it's a very simple trick. This is sort of nothing but a plate, two parallel plates which have some reflection, these are coated surfaces, which end up producing, this is known as an echelon effect, end up producing series of pulses coming out, and these series of pulses in fact can help in selecting out fluorescence of one with respect to the other. Because there are pulses which will come, which will excite one and then de-excite the other one, whereas in the other case that will not happen because they have different fluorescence, but they might have a same absorption place, so it can get absorbed. So you can play around with these things and you can show that you have advantages in microscopy. That is another application. And obviously there are cases where we can take it to molecular systems and we can look at coherence effects on molecular systems. This is an example where we had looked at fragmentation cases. I will not go into the detail of this because this I have just now showed you. It's just that the fragmentation of a molecule can have a very specific effect depending on how we are exciting it. So if we have a frequency changing going from one direction to the other, there can be a significant effect of that, and that can be used as a way of showing that. So this is actually plotted with respect to the second harmonic generation, which is symmetric on both the sides, but the fragment patterns are very specifically affected by the chirp parameter of the laser light which is being used. And so that could perhaps be an interesting handle that we could use. And this is one aspect. The other thing is that we, instead of using a chirp, that is a mechanistic aspect, we could also change the polarization of the light. Now this polarization of the light is, by the way, a macroscopic polarization of the light change, and so it means that it's essentially just modulating the intensity of the laser interaction. And if you would think it that way, you would think that it is only the overall number of ions which will be changing, and that's exactly what happens. You see an overall change in the ion yield rather than the ions becoming differently influenced. And so what you could do is you could use both of them, one or the other, and use them as exclusive controls for the development of these systems. So this is one of the areas. So in this Because when you look at how these things, this is important in our context also in quantum computing, because what happens is you would be wanting to have different controls at different levels so that you could do a proper gate or a proper manipulation of the quantum bit, and therefore having mutually exclusive devices controls are very important. So here is one more example I was thinking of showing you, which is to do with the chemical dynamics of the system. Now, this has been one of the major dreams of what chemists would have always wanted to do, is to see if you have a laser-driven reaction, and in this particular case, it's actually pentane molecule. So this molecule is a dimer, and so this is a dimerization reaction, then this is a falling apart reaction. The dimerization reaction is at room temperature. However, its falling apart is by laser. So the idea was to see if the laser interaction could be tuned in such a way so that you could have a control over this process. And so we did the same kind of a technique here, where we put the molecule come through this beam chamber, and we were looking at how this pulse interacts with it. So this is a very effective way of looking at this system, because we have only two fragments here. This is the parent fragment, and this is the two fragments which are being created because of their breaking apart. Under certain laser powers, it was possible to keep it only at the two fragments, but as you change the fragmentation power to a very large number, like 360 here, it actually starts showing other fragments. So we restricted ourselves to not to go to this limit. We were limited up to about 340 microjoules, where we were effectively seeing only the two fragments which matter. So under this condition, we did a few experiments here. So it actually shows that as you change the laser power, you can in fact see the ion ratios to saturate, and there are only two fragments which work here, and this is the place where we were remaining. Under this condition, we were able to show that the two slopes are close enough, but they are distinct, showing that the two reactions are mediated, the two are of a different kind. So this is because of the dimer, and the other one is because of the monomer. Now, dichloropentadiene is the name of the dimer, and cyclopentadiene is the name of the monomer. Now, as you can see, the autocorrelation is the pulse itself, and the falling part of the pulse of both the components are not too different. That means it's a very fast process. So we were able to resolve how this, so in this particular case we used two pulses. One was exciting the system, the other one was reading the system. And what you would expect is that when you apply, when you just use a second harmonics intensity, it will essentially just fall because it is just growing as you change the chirp, and that is symmetric. And similarly, your pulse width will just keep on increasing monotonically on both the sides, as expected. However, when you look at the relative ion yield, I'm sorry of the size over there, relative ion yield of the monomer product, which is the breakdown, which is laser driven, there is a major difference from the negatively chirped end towards the positively chirped end. The positively chirped end essentially follows exactly what the second harmonic generation part shows, in the sense that it is just an intensity dependent effect. However, this part shows that there is a major effect of the phase, that the chirp is negative. It means that the fragmentation increases, the ion yield of this product increases a lot compared to what is expected from the intensity alone effect. And so this particular result came out to be as an interesting part, which this actually is right now in press. It is coming out in the frontiers part of the chemical physics letters. So this is perhaps one of the few experiments where definitive control of a molecular breakdown has been shown, because most of the molecular systems which are shown to have a laser based interaction, reversible reactions are very hard to treat with, because whenever a system goes in one direction, it also has a probability to come to the other direction. It becomes very difficult to deal with it. So this was one of the areas where we could show that even the chirp of the laser has important results to do. And finally, the other area where we have been working on as a part of this development has been to do the spatial control, as we have been discussing. That is because, as I mentioned, maybe if we were only interested in chemistry or doing microscopy, we would not do. But since we have the desire to have a computing complete on a molecule and then transmit or have it translated to the next molecule or the system in a programmable manner, so it is to our benefit that we would like to control the center of mass motion, and that too with a single laser beam, so that the same laser which creates the interaction is also transmitting the information the moment the computation is over. So in this respect, we have basically used the basic idea of optical trapping, and it is just the photon flux which works, and this can be explained in terms of the gradient forces as well as the scattering forces which the particle faces when it is inside a focusing laser beam. Now, this is true for transparent as well as non-transparent conditions also, and in non-transparent conditions the equations are slightly different, but you can prove it that even in those cases the same idea of having a gradient and the scattering force, except that the refractive index issues will be different in those cases. So whatever way it is, you will see that the particle will be forced to come close to the focal spot, and that is what is done in most cases. What we have changed in our particular setup is that we have gone to a condition where the laser is no longer continuously operational, and that is because if we talk about information transfer, there has to be pulses, otherwise there is no information transfer. If it is a continuous laser, unless it is switched on or off, there is no information transfer. So having a pulse laser which has the information content, which is doing something to the system under interest, is ready, has done its job, and is now needed to go to the next level, it is important that the motion occurs on control of the laser, and therefore we had to show that it works for a pulse laser. Turns out that pulse laser also has given us another advantage. That is that with the pulse laser we get the additional nonlinearity of two-photon absorption, which then allows the simple two-photon fluorophore systems to be coated. So what we do is we take a bead. These are experiments which are shown on a simple bead particles. So these are about 1 micron latex beads, which are then coated with a dye. And this dye is two-photon dye. It's not a single photon dye. So which means that if you have 800 nanometer light coming in, nothing will happen to that bead. It will not absorb. But if there is enough flux of enough flux of light such that they are coherently connected, then the two photons will be absorbed and you see a fluorescence coming from the excited state. And that's why you can see it lighted up, and there is no need for having any other light to see this. You can just see the particle light up just like that. And that advantage in itself is very important, because that means we can do a background free detection, and that allows us to go to sub-diffraction limits for a particular case of using the trap. So under our particular trap condition, we can easily go to sub-diffraction limits and we can see nanoparticles. We have currently gone down to about 17 nanometer particle size, which for an 800 nanometer laser is much below the diffraction limit size. Because 800 nanometer would have been, whenever we talk about 100 nanometer particle size, we are already sub diffraction limit. So 17 nanometer size is really sub diffraction limit. Now the beauty of this is also that it gives us an interesting question where we now have a spatial trap, spatial quantum condition in some sense. We have a well which is there, and then it is not there, and it's there. And so this kind of an interesting situation means that the particle, when it's trapped, has a situation where it is trapped and then it is left without any field for a while, And yet, because the trapping field comes back within a given period of time, if the motion of the particle has not happened enough, then it will still remain trapped and you will be able to see it again. And that is the basic trick behind these kinds of principles. And typically, since these are intense pulses, these potentials, these spatial potentials which are created are very deep. And so if the particle falls in there, it has a lesser probability of coming out, and so it is more stably trapped. So we have essentially seen in chemical terms, maybe quasi bonds, because we are able to put more than two particles in potentials. Now these are diffraction, the sub-diffraction limit. So my potential is large and my particle is small. So it goes down, and there is enough room for the next one to go down too. So in fact, we have seen particles go up and being trapped together. This one, both of them have come out, but we have some pictures where only one of them have come up reversibly. Here. So this one goes up, stays there, then the second one goes in, and then only one of them comes down, and the second one is still there, and then the other one also comes out. So these are very interesting, and these are actually, if you look at it, the hundreds of seconds that they are living in there. And so for a period of time, you can think that there are hundreds of seconds where you had trapped two particles in the same spatial domain where they were too close to each other, and yet they were not bonded because they could come out and be on their own. So this level of control is something which we are currently looking at. So this is 16 nanometer quantum dot, which we looked at. But as you can see, the time over which we can trap here is a little bit harder. So this is about 120 seconds that we were able to trap it. And these kinds of experiments, I have to really give my students hats off, because generally this is a statistical process. And so you start the experiment in the morning and with the hope that it will happen, and maybe at midnight this event starts. So you keep all your setup, apparatus, everything working, and then suddenly it will happen once, and then you have to trap that data right away. Typically, the other way of looking at it is that we essentially have a continuously running computer program which sort of monitors it so that we never lose anything which is going on. Unfortunately, data today saving is cheap, so we can save millions of bytes without much of a problem. And last but not the least, I'll actually come to one of the other aspects which is kind of interesting in all contexts, which is the thermal effects. One thing which we often forget is that laser in itself is a huge thermal source, more so when you are in the infrared region, because you are talking about bullets of infrared radiation, which we all know when we go for therapy and all that. These are heat radiations. And so the thermal effect in itself can actually have an effect which can be of interest. And so one of the things which we have developed over the years is we are going towards thermal imaging. Thermal imaging is not new. Thermal imaging with infrared imaging is already there, but to use femtosecond light to do thermal imaging has its own advantages. One of the biggest advantages here, we are looking at reporter molecules or things which are at molecule level. Whereas when we do thermal imaging of today, which is mostly done by military and other, it's basically the thermal glow and all that. These are for macroscopic objects. So here we are trying to go to molecular levels. And so the question is whether it even works or not. And so here is the setup which it shows. We have actually a fiber laser. It's one of the oldest fiber lasers which is still working. In fact, this company representative who visited my lab never knew that this is sort of, I think, the serial number 2 or something which was made. And so they never thought that this laser can survive this long. This is more than 10 years now. It's about 12 years that it has survived, and it's still working. So anyway, they made it too good, which is good. So this has two wavelengths. This is the C band, which is the 1560. It was made for communication. And the other one is the double of that, which is 780 nanometers, 778 to be precise. No, this is 780. So what we do is we make an interferometer out of this, and so this is our thermal beam, and this is our reporter beam, which we use, and we do a thermal lens spectroscopy of this. And what we find is that it is very sensitive to the molecular aspects, and so we can do binary liquid mixtures where our reporter is essentially something like methanol. And these are also very important because many of these cases we don't have fluorophores. I mean, we need reporters, and in many cases we have difficulty in finding reporters. This particular case, something like a solvent can be a reporter, and solvents are everywhere. And like methanol is, for example, is a very useful solvent for many of the cases, and so it turns out that we can use this. This is a thermal study that we have done. We have now gone ahead to do a lot more interesting work, but I will not go into the details here. All I will just say here is that with methanol and water, we were able to show how sensitive the measure is, and although initially you would think that water would be a better thermal reporter, it turns out that methanol is a better thermal reporter compared even to water, and there are ways of proving why it is one way or the other. The other important part which we found was very exciting was that we could also find out that okay, so these are basically binary mixtures, and as you can see that there are cases where they will even have thermal responses which are higher than individual elements, and so that shows that there is some sort of a synergy which also occurs in these cases. In some senses, they can also be looked at as memory of the system, and so there are other ways of looking or interpreting these stories that we are now looking at it. But the most interesting thing after the BRC talk, it will be interesting, is to also see that it can distinguish isotopes, and this is a case where we have seen the water methanol versus D2O methanol, and there is this distinct distinction between their properties as we do a binary mixture study from these cases. So with that, I would like to conclude my talk here. I would say that I have benefited immensely from our association with this program, and two outputs. One of the major outputs which I think many of you have already gotten in your handout is a nano computing book that we together wrote with Vishal. Currently I am on sabbatical writing a book on quantum information processing with light. I was teaching a similar course for the last 6 years, and so I thought it was time enough to put them all together into some sort of a book, which currently I am writing. And there are other developments and issues that have evolved over the years of it, some of which I have tried to present to you. With that, I would like to thank you.